Hello everyone, today's video is on our worked example on single degree of freedom vibration system. In part 1 video, we'll learn how to find natural frequency of single degree of freedom system in 3 cases: undamped, damped, and free and forced vibration. In part 2 video, we learn how to draw time domain response of vibration signals qualitatively. Let's apply these concepts to solve our example. So this is our work example we need to solve, which consists of 2 pulleys. They are attached through a belt. A piston is attached to the bigger pulley through a cable. A spring and a damper is attached to the piston. External moment MT is applied through to the system through a bigger pulley, and a point mass is attached to the bigger pulley. We consider that the pulleys are of uniform disc and the belt and cables are ideal, meaning they are inextensible and they have no friction. And it says that when this is the uniform, this is the equilibrium position. That means in that position, no external moment is applied. The values are given to the for this system to you for calculation. So we need to find nonlinear equation of motion using theta equal theta 1, rotation of small pulley as a coordinate. We need to find static elongation of the spring. We need to calculate the system's natural frequency, damping ratio, and damped natural frequency. Also, we need to draw the free vibration in time domain. Finally, if an external moment is applied on the pulley M2 with expression MT equal MO cos omega t, write the expression of steady state vibration amplitude. Just a quick review on how to approach a vibration system, particularly for single degree of freedom. In part 1 video, step 1 to 5 were introduced to you, where in step 1 we need to draw free body diagram. Please remember that for free body diagram we need to draw each body separately. Let's draw free body diagram for the system. So this is the system. We need to draw free body diagram separately. Let's start with pulley 1. So in pulley 1, 2 reaction forces acting at the center of the pulley, and weight is also acting on the center of the pulley. T1, 2 and these T1, 2s are belt force acting on the pulley. Similar way, we can get similar kind of force on pulley 2, except that T24, which is a cable force, acting downward. Okay, and then we need to consider point mass. Where is this? So again, point mass is connected to the bigger pulley through a pin joint. So at center of the point mass we have 2 reaction force, and at the center of the point mass also force weight is acting. Last, free body diagram is of a piston. So the piston has 2 cable force, upward which is going to the bigger pulley, and downward is going to the mass and spring, and we name it as TMKC, which is cable force from mass to spring damper. And also center of this piston weight is acting. In step 2 we need to write forms of energy equations for each component, and in step 3 we need to express all kinematic quantities as a function of selected coordinate. As first part of question asks to consider rotation of small pulley as theta, so we need to express all kinematic quantities for this system as a function of theta. This part is very important to get right form of equation. To make the calculation easier, we'll do step 2 and 3 together for this system. Let's consider how the components will move if small pulley M1 rotates counterclockwise at an angle theta 1. Then the bigger pulley will rotate at the same direction of small pulley with an angle theta 2 counterclockwise. So the piston will move downward. As a result, spring and damper will be shortened and the point mass will move upward. Start with kinematic energy. Since pulley 1 and pulley 2 will rotate only rotational direction, so we'll have only kinematic energy for these two pulleys. So we can write half J1, which is a mass moment of inertia for first pulley. J2 is mass moment of inertia for second pulley. So the expression becomes half J1 theta 1 dot squared plus half J2 theta dot 2 squared. Now for point mass M3, we'll have only linear motion. That's why we'll have only linear kinetic energy. Same case for piston M4. So we write half M3 V3 squared and half M4 V4 squared. Let's express all the kinematic quantities as a function of theta, as we mentioned earlier. Starting with J1 and J2 are mass moment of inertia for pulley or disc, which is half M1 R1 squared. That means mass times radius squared times half. So half M2 R2 squared for bigger pulleys. As the question said, we can consider theta 1 equal theta. So we can write theta 1 dot equal theta dot. For if we consider these two pulleys which are connected to a belt, so we can write velocity of the belt, linear velocity of the belt can be written as theta dot times R1. That means for smaller pulley. Same kind of expression we can write for bigger pulley, which is theta 2 dot times R2, and this can be then equal to theta times R1. So from this equation we can write theta 2 as ratio of these two pulleys times theta 1. Now the linear velocity for point mass M3 will be V3 equal L3, which is the distance from this revolute joint or point of rotation to the center of the point mass, L3, times theta 2 dot, that means angular rotation of the second pulley. Since we already know that the expression for theta 2, we can write L3 times R1 by R2 theta dot. By the way, we get here positive sign because both pulleys are rotating in the same direction. They would be negative if they would rotate in opposite direction. Alright, so that's our V3 expression, and for linear velocity for a piston M4, we can write V4 equal, again the distance from the rotation axis or center of rotation to this mass, which is radius of pulley 2 R2 times theta 2. Again, if we want to write down the expression would be look like this: R1 by R2 theta dot, as a result R1 theta dot. Now since we get all the quantities, let's now substitute these values into kinematic energy. So after substituting all the kinematic values, the equation T becomes look like this, where underlined quantities are substituted value. Since all term has half and theta dot squared, so we keep these two out of the bracket, and other values we keep into the bracket, and let's consider inside the bracket quantities as J equivalent to make the equation simpler. And that's our T expression or kinetic energy which is half J equivalent theta dot square. Let's differentiate it with respect to time, which becomes half J equivalent to theta dot dot. That becomes J equivalent theta and theta dot dot. Alright, now we need to consider gravitational potential energy Vg, which is we only get those components for gravitational potential energy which have linear kinetic energy. Since M3 and M4, which means point mass and piston, has linear kinetic energy, so we have gravitational potential energy for these two components, which is M3G del H3 plus M4G del H4. Let's consider M3, which is you already have seen that the distance from the center of rotation to the center of the point mass is L3, which is given to you. Now when the point of mass moves upward, it becomes L3 cos theta, because this is the theta, and so this expression or this length will be L3 cos theta, and we want this height, which is del H3. So del H3 can be written as del H3 equal L3 minus L3 cos theta. In case of del H4, we can write R2 theta 2, which becomes R1 theta. You already know the expression. Now it will be negative. Why? Because the piston is moving downward. Alright, so now substitute these two values into this equation. The equation become M3G L3 minus L3 cos theta plus M4G times negative R1 theta. If you can just notice that the point mass was attached to the pulley 2, so the angle of deflection will be theta 2, so our expression will be L3 cos theta 2. So the expression we'll have is L3 minus L3 cos theta 2. And we already know the expression for theta 2, which can be written like this: M3G L3 minus L3 cos R1 by R2 theta, and that's our expression for, that's our complete expression for point mass. Then we differentiate this form of gravitational potential energy with respect to time, and we get this kind of expression. Alright, so for elastic potential energy Vk, we can write half K del Lk squared, where K is the stiffness, spring stiffness, and del K is the spring displacement. If we just look, consider this spring diagram, where when the spring was at initial elongation or displacement, we consider this is a del Lk static. This is static deflection of the spring. Then when the piston moves downward, the spring become shortened. That deflection we consider as del Lk, and the shortened displacement was negative R2 theta 2, negative because it is shortened. So we can write del Lk, which is deflection of spring, as static deflection of spring negative R2 theta 2. As we already know the expression for theta 2, we can write directly R1 theta. Now substitute this value into this equation. We can get half K del Lk static minus R1 theta whole square. Now we want to differentiate this Vk with respect to time, and we get K del static deflection minus R1 theta times negative R1 times theta dot. The deflection of damper will be similar to spring. At equilibrium position, we get static deflection of damper, which is del LC ST, and when the damper was shortened, we get the deflection as del LC. The amount this damper shortened was L2 theta 2. Because the damper shortened, that's why we get negative sign. So let's write down the expression for del LC, which is del LC static negative R2 theta 2, and we know the expression for R2 theta 2, which is del LC ST minus R1 theta. Now we want derivation of deflection of a damper, so we take the derivation of it, which becomes R1 theta dot. So now let's replace this value into the equation, which becomes negative C R1 squared theta dot squared. Last expression is for power due to the external moment, which can be written as mt times theta dot 2. Theta dot 2 because the moment was applied to bigger pulley, that's why we take the angular rotational displacement of that pulley. So we just write the expression for mt, which was given in the equation as mo cos omega t times, and we know the expression for theta 2, which is R1 by R2 theta dot. Next step is to find nonlinear equation of motion. So these expression we get when we consider damped free vibration, and in case of damped forced vibration we have external moment or external force part on right hand side. Because our system is damped force vibration, so we have this we'll have this expression, and we already get all the values, so we can just substitute these values and we get this kind of expression. And this is our first answer, which asks us to write down nonlinear equation of motion considering theta 1 equal theta. Next step is to linearize the equation of motion. So the first step of linearize the equation of motion is to assume angular deflection is so small that we can consider sin theta equivalent to theta and cos theta equivalent to 1. So substituting this value into our equation, we get this form where R1 by R2 theta. Now the second step is to considering static equilibrium position, where we know theta is 0, so angular deflection and angular acceleration as well as angular velocity will be 0, and as question asked us to consider no external moment at initial level, so mt will be also 0. So considering static equilibrium, all terms will be 0 except these two terms, where we get the expression for spring static deflection, and this is our second answer. We get the static elongation of the spring as the values are given, so we can find the static deflection of the spring, which is negative 9.81 millimeter. Now we want to replace static deflection of spring into the equation, and then we get this form of equation where these two terms will be cancelled out and we'll get a simpler form of equation. Now if we just rearrange the equation and then consider this part is equivalent, this part as C torsional equivalent or coefficient of damping, this part as K torsional equivalent, which is stiffness coefficient, and this part as moment equivalent, then the equation we get this, this is the final equation. So if we get this kind of equation, then from this equation, by definition, we can write natural frequency as root over K torsional equivalent by J equivalent, damping ratio as C torsional equivalent by 2 omega n J equivalent, and damped natural frequency as omega n times root over 1 minus zeta squared. Since all values are given to us, so we can find J equivalent, K torsional equivalent, and C torsional equivalent, and we get these values. Please feel free to pause the video at this moment and just calculate and match with these values. So when we get these values, we can find natural frequency of this system as 19.12 radian per second, damping ratio as 0.095, which is less than 1. So we can consider these cases under damped case, and we can find damped natural frequency as well, which is 19.09 radian per second, which is obviously less than natural damped frequency. So this is our third answer, where we are asked to find natural frequency, damping ratio, and damped natural frequency. As our case is under damped case, so we get this kind of expression, which we already know, and this is the general equation, general response for the undamped case, and the period of damped natural frequency would be this one. So we calculated, which is 0.33 seconds, which is our third answer. Let's draw this diagram for our case qualitatively. Okay, so qualitatively we can draw this diagram where this dotted line is the negative exponential part of the equation, which is negative zeta omega n times t, and for this part the amplitude of the vibrations eventually decays, and this one is the resultant response theta, which is which has amplitude, which has negative exponential part, plus which has cos component part, omega d t plus phi. Okay, and the damping time period, as we already calculated, which was td equals 0.33 second. Our next step is to solve linearized equation. So if we want to recall our system equation, which is this form, so this equation can be said as non-homogeneous second order differential equation, and for this kind of equation we get the solution as theta equal theta h plus theta p. Theta h being this homogeneous or complementary solution of free vibration equation, which can be expressed by this equation, and theta p being the particular solution, which is mainly occurred for force or moment, and the expression can be for particular solution is this. So as we say that this expression actually decays after a while, where this expression is continues as long as the force continues. So we are more interested on particular solution. So the particular solution, now we want to know the amplitude of particular solution, which is theta p, and which is given by this equation. Now if we want to consider our case, so our case we get this kind of expression, where this numerator part we get it from our system equation, moment equivalent, which is MO R1 by R2, so MO R1 by R2 K torsional equivalent. And that is our last answer, which where we asked to find expression of steady state vibration amplitude. If we want to vibration graph qualitatively, which will look like this part is called transient solution and this part is called steady state solution, and this equation is the representation of this curve. But this steady state solution is consist of only particular solution, which can be expressed like this, and we already know the amplitude for our case is like this. And this transient solution is consist of a particular part as well as a homogeneous part, and this homogeneous part, if we just look at this equation, we can see that it actually fades away eventually. So and this can be expressed by this equation. Hope that will help you. Thanks for watching.